have the definition of a limit up here, and I also have this theorem. Suppose you have a function domain A and C is the limit point of A. The following are equivalent. The limit as x goes to c of f of x equals L is the same thing as if and only if for all sequences x sub n contained within the domain such that c does not appear in there, and x sub n goes to c, then it has to be true that f sub x sub n, that's barely legible, f sub x sub n has to converge to L. Right, so I mean x sub n, right, it might be 1 over n, and maybe your f is f of x is x squared. Then f of x sub n would be f of 1 over n, which would be 1 over n squared, which is a sequence in of itself. So so basically 1 over n squared would have to converge to the limit if 1 over n converges to c. So that's basically what it says. These are both sequences. So why is this theorem useful? Well, it converts this talk about limits to things which have to do with, like, you know, an uncountable number of things and it's messy, to sequences. Sequences are nice to work with because they're countable. So that's the benefit of this, is that if we can change you know, the thing from functions to sequences. The cost is that we have to make it true for all sequences, which is the difficult part. So we don't get everything for free. But here's the basic flavor of the proof. Assume that the limit is L. Now I need to prove for all sequences and x sub n a valid sequence, meaning that it fulfills number 2. Right? I need to prove that f sub x sub n minus L is less than epsilon for some capital N. Well, here's what I know. I know that because limit of f of x equals L, there exists a delta such that x minus c less than delta implies f of x minus L is less than epsilon. So here's what I'm going to do. Right? My x sub n's converge to c. I know that there exists a capital N such that since x sub n converges to c, I'll make sure that there exists an n such that this is true for all n bigger than or equal to n. Now what I've done here is normally you'd put an epsilon here. And it is an epsilon, except I'm taking my epsilon to be whatever that delta is. So when this is true, so there exists an n such that this is true for always. But if this is true, then the definition of function says that whenever you get this, you get that the f thing holds. But then f sub x sub n, this particular x, minus L, is less than epsilon. So we're done. So I've proved that this sequence goes to L. How do I do it? Right, I start with a valid sequence, and then I use the fact that the limit that the function converges to L, or that has a limit of L, to get my delta. So my delta is fixed now. So now I'm going to use the fact that x sub n converges to c to get a capital N, such that x sub n minus c is less than, I'm going to pick my epsilon in quotes equal to delta for all capital N less little n less than equal to, bigger than equal to capital N, sorry. So once this is true, that means that x sub n minus c is less than delta. Well, whenever you have any sort of an x minus c is less than delta, that automatically gives you that f of whatever minus L is less than epsilon, which gives you that this is true, or I should say for all n bigger than or equal to capital N. So in order to prove that this limit holds, I need to find a capital N such that f of x sub n minus L is less than epsilon. Well, the epsilon is given at the beginning, and that holds, and it's true for all the capital N that happen to be the same as the capital N there. So stay tuned for the second half of the proof.